All right, let's get started then. Let's do about the last talk of today's workshop. As a reminder, if you didn't hear earlier, we're planning to go to Jupiter at 4:30. So if you want to join, meet us at the entrance then. Otherwise, take it away, Ray, where you can talk about, tell us all about list-decoding.
Thank you. First, thank you to the organizers for inviting me, and thank you all for being here. So this talk is about list decoding, so I'll start by giving an introduction to list decoding, and then I'll tell you about the classic result in list decoding, which is the list decoding capacity theorem. And then I will tell you two stories in list decoding, one about list decoding random linear codes, and another about list decoding read-solved codes. So you're all at a coding theory workshop. You all know what an error-correcting code is. Here's a sentence. You can figure out what it's supposed to say in spite of the errors. That's what we want in an error-correcting code. And generally, how do we set it up? We imagine a communication context where Alice wants to send a message to Bob, but there's a noisy channel. So if she sends the message directly, Bob gets the wrong message. So she uses an error-correcting code, adds some redundancy, so that even in the presence of noise, Bob can still recover the original message. So in this context, we think of the code as a code is a set of strings. We think of the code as the set of possible things that Alice can send. And in this talk, we care about codes that are subsets of fq to the n, so we think of them as vectors over some finite field. Right, so everything we care about, or a lot of things we care about, are captured by this code C. And a lot of things we care about the protocol are captured by the code. Of course, we also care about efficient encoding and decoding. We don't worry about that in this talk, so we just study the set of strings. So what things do we care about? Well, we want the code, one, to have large rate. The rate has this definition. It's log base q of the size of the code divided by n. You can check C is at most q to the n, so this is always between 0 and 1. And bigger rate is generally better because that means Alice has to blow up her message less. In this talk, we'll deal with linear codes, so C is a subspace, not just a subset of fq to the n. So in this case, the rate has this nice formula. So of course, we want codes with large rate, and we also want noise tolerance. And there's a lot of ways to define noise tolerance in coding theory. We consider list decoding in this talk. So the definition is here. We say a code is p comma l list decodable if for any vector z, the Hamming ball around z of radius p times n has at most l code words. So here, think of p as a number between 0 and 1, which represents roughly the fraction of symbols that are corrupted, and l we call the list size. Think of it as a constant like 1, 2, 3, and so on. So how should you think about this result? I give you two interpretations. One is this is just a geometric result about a set of points. You think of our code as a set of points in fq to the n, and this definition says that these set of points are not too clustered, in the sense that no small ball contains too many code words, so they're kind of well spread out. So it's this combinatorial geometric definition, but it's also has applications in this communication setting. Here, you think of Z as whatever Bob receives. So this definition says that for anything Bob receives, there's at most L code words it could have come from if at most Pn errors were applied. So this is saying Bob can always produce a list of L messages containing the correct one. The last thing to note is that this is true for any Z, so this is a statement about worst case or adversarial errors. So this is the list decoding definition, and so list decoding is important both in theory and in practice. Notice that if you put in L equals 1, this is probably the coding theory setup you're more familiar with, where this is unique decoding, and those of you who think in terms of distance, this is P roughly is half the distance. And so why do people care about list decoding when, obviously it'd be nicer if you get the message exactly? Well, in general, what do you get from this relaxation of Bob only has to produce a list containing the correct answer? You can tolerate more noise. So the rough intuition, and this is very hand-wavy, but this is the intuition you should have, is that if you relax from unique decoding to list decoding with some large constant list, you can tolerate roughly twice as much error. And because of this, list decoding finds applications in a variety of contexts where you need to tolerate noise, and you might have other ways you can deduce the correct answer from the list. List decoding is important in practice, also important in theory. Remember, our list decoding definition is just combinatorial geometric definition about a set of points in f(q) to the n. And because it is this fundamental definition, it finds these extraneous applications in contexts that have no obvious need for error correction, like in complexity theory, cryptography, pseudorandomness, and so on. So list decoding is important in theory and in practice. So what is known about list decoding? The classic result in list decoding is this thing called the list decoding capacity theorem. And so in any error correcting code setting, we ask, what's the optimal trade-off between the noise tolerance and how non-redundant it is. So what is the optimal trade-off between the rate and the error tolerance? And so this is known, and it's known basically as old as list decoding itself. Here, we want to trade off R and P, and we're happy as long as L is something reasonable, like a constant or even polynomial in N. And in this setting, the optimal trade-off is known. So if we restrict ourselves to binary codes where Q equals 2, the alphabet size is 2, then the optimal trade-off is this R equals 1 minus h of P, where h of P is the binary entropy function. So what does it mean that this is the optimal trade-off? Well, if we are just below this trade-off, that means we can list a code with constant list size. So there exist rate 1 minus h of P minus epsilon codes that are list decodable to radius P with list size 1 over epsilon. On the other hand, if you're just above the trade-off, then your list size needs to be exponential n, so you can't do much better than true. The trade-off is known for binary codes, and also you could ask what happens if you don't put any restriction on the alphabet. In this case, the trade-off is also known. It's R equals 1 minus P. So this is great. So we know the optimal trade-off. So then, one issue here, or the big issue here, is that the proof that these codes exist is non-constructive. It's one of these early applications of the probabilistic method. And the proof is literally, you want a code of rate R, so you sample 2 to the R times n code words independently at random, and you show the resulting code is list decodable with high probability. So it's straightforward, fits on a page. And the upper bound is just a counting argument. So the proof that these codes exist is non-constructive. So the main goal in list decoding is to find explicit list decodable codes that achieve these optimal trade-offs. And as computer scientists, we like to call this the problem of finding hay in a haystack, because most codes are good, but then somehow picking out one explicitly is challenging. And for those of you who've never seen this before, how could it be so hard to find hay in a haystack? Well, another analogy I like to say is, imagine I give you the problem of going to outer space. If I use the probabilistic method and pick a uniformly random point in the universe with high probability, I think I land in outer space. But if I start from planet Earth, you have to build a rocket ship to get there. And I think finding explicit list decodable codes is probably easier, not as hard as building a rocket ship, but the analogy illustrates the difficulty. So I'll tell you 2 stories that are towards this goal. So some of you are probably thinking, okay, well, we do have explicit list decodable codes, so I will get to that. But I'll tell you 2 stories about list decoding random linear codes and list decoding Reed-Solomon codes. So first, I'll talk about in the binary code setting, and then I'll talk about the large alphabet setting. So this is based on joint works with Mary Wooters, Venkat Guruswamy, Jonathan Masheyev, Nicholas Resch, and Shashwat Sainis. So the question for binary codes is, can we find explicit rate 1 minus h of P minus epsilon codes that are list decodable to radius P with list size something reasonable? And this was open when we started the project. This is, as far as I know, still an open question. So very important and tantalizing. What we study is something more modest. So we study how list decodable is a random linear code. So a linear code is a subspace of f2 to the n. Random linear code is a random subspace. So random codes, random subsets are optimally list decodable. What about random subspaces? So we could ask, is this an RLC, random linear code of rate 1 minus HP minus epsilon, list decodable up to capacity? So why would this be important? Well, one thing is it's a de-randomization result, right? The uniformly random code needs exponential and n random bits. This needs, a random linear code only needs quadratic random bits. So we're making our haystack smaller. It's also this purely geometric mathematical question about how clustery is a random subspace of f2 to the n. Remember, list decoding is just a property about being clustery or non-clustery, and so it's a geometric question. Random linear codes are also used in other code constructions as building blocks, so they're important to study in that sense. And some follow-up works to the line of work I'll be talking about shows that random linear codes are typical in the sense that anything you can show for random linear codes, you also get black box for other random ensembles of codes like LDPC codes and punctured low bias codes. This is some work by Mosheev, Resh, Ranzui, Silas, and Wooters, and then Guruswamy and Mosheev. And lastly, random linear codes also come up in other questions, like list decoding random linear codes come up in other contexts, like learning parodies noise and learning with errors. So hopefully I've convinced you this is an important question. So what is known about this? So randomly, let's see. So it is known, okay, here we go. So the question is a random linear code of rate 1 minus h of p minus epsilon list decodable to capacity? And it's been known for a while that the answer is yes. So this is an argument of Zyeblov and Pitsker, and they show that they are list decodable, but they're list decodable with list size 2 to the power 1 over epsilon. So remember before, the list size was 1 over epsilon for random codes. Here you get 2 to the 1 over epsilon. And the argument is very similar to the random construction. You just figure out what's your bad case. You have bad list decoding configurations, and you union bound over you bound the probability that happens, and then you do a union bound and get your result. And the reason you lose this exponential is because when you have a random linear code, the code words are not necessarily independent, but among any 2 to the 1 over epsilon code words, you have 1 over epsilon that are linearly independent, which is why you get this blow up. So we are list decodable to capacity, but a natural question is, can you be list decodable with linear and 1 over epsilon list size? And this is a question asked by Elias. And so there are a couple of different works in this direction. So first, Guruswamy, Hastad, Sazan, and Zuckerman showed that you can be list decodable with list size 1 over epsilon, but this is just an existential result. So they showed that there exist codes, linear codes that are list decodable with list size 1 over epsilon. Then there were these two works by Guruswamy, Hastad, and Kaparti, and Wooters, who answered affirmatively Elias's question. So these two results together showed that random linear codes are list decodable with list size O of 1 over epsilon. The first result holds when p is bounded away from a half. The constant blows up as p goes to a half. And the second result holds when p is close to a half. So when you piece these two results together, you qualitatively get answer Elias's question. So this is great. We've answered the question, but there were two things that were somewhat unsatisfying here that motivated our follow-up work. One is that, okay, the constant is not optimal, but okay, who cares about constants? The other thing is that we're trying to get this one qualitative result that random linear codes are as list decodable as random codes. But to get that, we have to piece together these two very different arguments. And it would be more mathematically satisfying if we could have one argument that gets just the whole thing in one shot. And so that's what we do. So this is my work with Mary, where we showed that random linear codes are indeed as list decodable as random codes, and they get list size 1 over epsilon, and in fact, something better than 1 over epsilon, h of p over epsilon. So h of p is always less than 1. So this is a bit better. And we get it with high probability. And the way we do it is we extend these ideas from the Guruswamy, Hastad, Sedan, and Zuckerman paper. Furthermore, after this, with some other collaborators, we discovered that using pretty different techniques, that the bound we got here is actually really tight. So we showed that a lower bound that says random linear codes with high probability are not list decodable with list size that is just maybe 3 less than the upper bound that we got. So in particular, it shows that the bound we got on the list size is really tight. And so sort of we kind of got the right argument for this. Another way to think about this is this is saying that if you take a random linear code and ask what is the list size L such that it's optimally list decodable, this L is concentrated on 2 or 3 values. So it's kind of analogous to similar results in random graph theory where the diameter or the chromatic number is concentrated on 1 or 2 values. This is the story for random linear codes. Basically, for list decoding random linear binary codes, the question is settled. We kind of have the right answer and down to a very precise, fine-grained understanding.
And for the general linear codes and random nonlinear codes, what's the status?
Sorry, for general linear codes.
Not necessarily random. Then this lower bound is not 1 over epsilon.
So what's the lower bound if you have a general linear code? Yeah, so I think this is at least if you have a general code and you ask what is the optimal list size, you think there's a lower bound of 1 over epsilon, but actually in general, we only know log 1 over epsilon, but I think everyone believes it's 1 over epsilon. Yeah, this lower bound is just a high probability lower bound for random linear codes.
Random general codes?
For random general codes, the lower bound is 1 over epsilon. We proved that in our paper.
Without the HFP.
Without the HFP, so they're actually better.
Yeah, Rudra have something earlier, maybe I may be mistaken, but for random codes.
I think, I don't know if that one might have been omega 1 over epsilon as a lower bound. So the story for random linear binary codes is settled, but one thing that is very tantalizingly open about this is what happens for non-binary, even q equals 3, 4, 5, 7, and so on. So a lot of these results actually do hold when you go to larger alphabets, but this nice upper bound that we got here doesn't seem to generalize to all q, or at least we haven't figured out how to do it, and I think several others have tried. It seems very elusive, and so this is a tantalizing open question. It would be very interesting if someone could generalize this either with our techniques or something else to all alphabets. The lower bound holds for other q's, but the upper bound somehow, yeah. Yeah, it's HQ of P, yes. That's the lower bound.
Is that the one that uses the potential function?
Yeah, so the upper bound is what uses the potential function. So I'm not going to go over the proof, but I'm flashing the slide. This has the whole proof on the slide, and this is more to say that the proof is not complicated, and if you had an hour, you could fill in the details here. So it's the high level idea is we have this potential function and we grow the code, one basis element at a time, and you track this potential function and you show that it doesn't grow too much and the whole code is list decodable. But I'm happy to talk about this more offline for anyone who's interested.
About your open question.
Yeah.
Is it possible that Reed-Muller codes achieve this, or?
Is it possible that Reed-Muller codes achieve, sorry, for the explicit construction or for this? That's a
capacity, right? So
the distance is really bad. I don't
is
think
it bad?
they have good worst
I
case.
think the
That
list sizes
doesn't
are
affect
known
list.
for Reed-Muller codes, and I think there are pretty tight estimates of the list sizes for Reed-Muller codes, and I don't think they achieve capacity.
And the distance is terrible.
Yeah, like worst case, it's like all this for worst case errors, Reed-Muller codes aren't correct.
The distance may not matter so much.
Yeah, it might not. But I do think
The
there's.
Reed-Muller codes, I think that the list sizes are quite large as soon as you get beyond the distance.
But beyond distance, I think.
Well, yeah, thanks. That's a good discussion. All right, so if there's no other questions, I'll move on to the other story, which is what happens over larger alphabets. So over larger alphabets, when there's no restriction on the alphabet size, the capacity is 1 minus p. So the question is, can you have explicit rate 1 minus p minus epsilon codes that are p-L list decodable with constant list size? So in this case, we do know explicit codes that achieve capacity. There's been a long, successful line of works, and I'm pretty sure I'm not citing everything here. But these go, if you've heard of folded Reed-Solomon codes, I mean, Prahlad talked about it this morning, folded Reed-Solomon codes, multiplicity codes, algebraic geometry codes, and expander techniques, and so on. This gets all of these things, is a very exciting line of work that gets explicit codes that achieve list decoding capacity in this alphabet-independent regime. So what we study is list decoding Reed-Solomon codes. So why is this interesting? Well, first, almost all, or maybe all, I'll just say almost all to be safe, of these results codes are generalizations of Reed-Solomon codes. So first, what are Reed-Solomon codes? Reed-Solomon codes are the most classic algebraic error-correcting code. So to define a Reed-Solomon code, you fix some evaluation points, alpha 1 to alpha n, in some field fq. And so here, now your field size needs to be bigger than n. And the code is defined as evaluations of low-degree polynomials on these evaluation points. So you pick your favorite low-degree polynomial, you evaluate it at alpha 1 to alpha n. Like here's a low-degree polynomial, we evaluate it, and then the sequence of evaluations gives us one code word. You do this for all low-degree polynomials, you get your whole code. So there's one code word for every polynomial. So Reed-Solomon codes are one of the first algebraic codes. They're very natural. So the natural question is, are Reed-Solomon codes themselves optimally list-decodable? There's these generalizations that are list-decodable, but what about Reed-Solomon codes themselves? So it's a natural question. They're ubiquitous. They're simple. They're optimally unique decodable, making them a good candidate for list decoding. So what happens for Reed-Solomon codes? So this slide is the literature, and so this is the story of what happens. So I'll plot the things down here. So we've got rate here and p on the other axis. And here I'm going to write p as a function of r rather than the other way around, just because that's more often how it's shown in the literature. And so the question is, are Reed-Solomon codes optimally list decodable? The singleton bound, or you could also say the list decoding capacity theorem, says you can't list decode in this region. And Reed-Solomon codes are optimally unique decodable. This is a well-known fact. And so that means you can list decode, in fact, unique decode up to radius 1 minus r over 2. And the Johnson bound implies that for free, just from the fact that they're unique decodable, they're also list decodable up to radius 1 minus square root r. Right, so this comes for free. You don't use anything up. You just use the fact that the code has distance. And a famous result of Guruswamy and Sedan says that they're not only list decodable, but you have efficient list decoding algorithms. And then this was the best we knew for a long time. And for a while, people actually believed maybe, or there was a lot of evidence that you can't go beyond the Johnson bound. So for example, if you have a full-length Reed-Solomon code where q equals n and alpha 1 or alpha n are just all the field elements, then you can list decode much beyond the Johnson bound. And there's some other works too that sort of have similar qualitative implications. But then there was this result of Rudra and Wooters that says that if you take a random Reed-Solomon code, what is a random Reed-Solomon code? It means you take a large field, so q is bigger than n, and you take n evaluation points independently at random. Then with high probability, these codes are, the resulting code is list decodable just beyond the Johnson bound. So okay, this is a big complicated expression, so how should you think about it? Think about it as 1 minus O tilde of r. So 1 minus r is better than 1 minus square root r, and there's some log factors, so this really only works in the small r regime. But if r is sufficiently small, this beats the Johnson bound. So there's some evidence that you actually can beat the Johnson bound. Then there was this work of Shangwa and Tamo that showed that you can beat the Johnson bound even for large R, so they get list decodable ability of, again, random Reed-Solomon codes up to radius 1 minus R times 3/4. Then with Zeu Guo, Chong Shangguan, Zaki Tamo, and Mary Wooters, we showed that they're list decodable up to this radius 1 minus O tilde of R. And so this is like this result, but we also beat the Johnson bound for constant R, not just subconstant R, because there's this Q factor up there. And then these two works shave the log factor. And finally, there was this breakthrough work of Brackenseek, Gopi, and McComb that showed that you, in fact, can list decode Reed-Solomon codes all the way up to capacity. And again, all of these results starting from here, these are all for randomly punctured Reed-Solomon codes, where you take a large alphabet Q, you pick n evaluation points at random, that's your code.
Like some of the results, like the fourth from bottom, is actually for L equals 2.
Yes, that's right. That's right.
This size comes into play.
Yes, right. So the list size comes into play, and so these are, so I simplified it to put it all on one slide, but they actually get something stronger here. They get list size 2 or 3. Yeah. Okay, that is a good point. So we have this result that Reed-Solomon codes are optimally list-decodable all the way to capacity. But one drawback of this, or one thing about this BGM work is that they show it over exponential alphabet size. So what they do is you start with Q, alphabet size that is 2 to the O of n. Actually, it's 2 to the O of L times n. And then you pick n evaluation points at random. And so the question is, well, could you start with a smaller alphabet? Could you start with, polynomial in n or even linear in n? And Guo and Zhang, so let's see. So this result, they get exponential in n alphabet size, but they also get exactly the right list size. So this is literally the best list size that you can get. But Guo and Zhang observed that if you relax the list size just a little bit, then you in fact can bring the alphabet size down. Okay. So they bring the alphabet size down to quadratic, and then with Venkat Guruswamy and Omar Arabia, we bring it down to linear. So yeah, and just to say this point again, this list size is literally the best that you can do. So there's a lower bound by Shangguan and Tamo that this is the best you can do. So we get linear in n alphabet size. It's an open question to prove that this is the correct constant. So that's interesting. Although we have some good evidence that the constant is near the best possible. So if you just look at the list decoding capacity theorem, it says that the alphabet size needs to be 2 to the 1 over epsilon without the times n. But all of these two results hold even when epsilon is subconstant. So if epsilon is less than, 1 over log squared n, then it says this is the best possible dependence. So maybe it should also, that's evidence it should also be optimal when epsilon is a constant. So all of these results give that Reed-Solomon codes are list decodable up to capacity with optimal good list size, and after all of it, you also get linear alphabet size. In fact, all these results, in fact, get something more fine-grained. So you could ask, well, what about? So this is we can get up to capacity with some large, 1 over epsilon L. But what if you wanted L to be, 1 or 2 or 3 or 4 or your favorite constant? All of these results also hold in that setting. So when L is fixed, there is something analogous to the singleton bound. It's called the generalized singleton bound in the literature. And it says that for a fixed L, you can list decode up to radius 1 minus r times L over L plus 1. So if you plug in L equals 1, this is just the usual singleton bound. It's 1 minus r over 2. So it's sort of some evidence that's the right bound. And so all of these results also hold in the fixed L setting. Okay? So you fix L, and so the BGM result says you can get all the way up to exactly the generalized singleton bound, but you need exponential alphabets. And that's actually, you can't do better than that. You need, that's inherent. And then Guo and Zhang, and then later our work showed that if you relax by epsilon, then you get polynomial or linear in n alphabet size. And so this is really the kind of the way the main result is stated initially, and then these results are all just corollaries. Again, this 1 minus r times L over L plus 1, this radius is the best possible, just by a simple counting argument. And you could ask, well, is the alphabet size the best possible? And this argument from just the list decoding capacity theorem doesn't work in this refined L setting. And in the follow-up work, Omar and Venkat and I showed that, in fact, you need an exponential dependence in 1 over epsilon.
And this is for Reed-Solomon or for everything?
Oh, sorry. These two lower bounds are for everything, and these, yeah, all the lower bounds are for everything. Yes.
Is the dependence on L that you're hiding really bad, or should it be like L over epsilon?
Right here, yes, the dependence on the L that we have here is not great. It's I think it's like 1 over 2 to the L or something. 1 over exponential in L. Although I think if you're proving a lower bound for average radius list decodability, we get either 1 over square root L or 1 over L. I think in the general case, the constant is bad. In other cases, it's polynomial. So at this point, it would be good. I'll also mention some follow-up work that uses similar techniques or other things you can do with these techniques. So these are all for randomly punctured Reed-Solomon codes where you choose the evaluation points at random. In the same work, we observed that everything you can do here also works for random linear codes. So here we show that a random linear code of rate, of rate r is list decodable up to the same radius. And here we get the optimal alphabet size O of 1 over epsilon with some suppressed dependence on L. And after our work, there is a work of Brakensikdar, Gopi, and Zhang, who showed that you can also get the same kind of result with randomly punctured algebraic geometry codes. So you take a certain type of algebraic geometry code, and then you pick some random subset of the evaluations, and you get the same kind of list decoding guarantee. So this was all, I guess I should cite another work. So they combine some techniques here with also a more general GM-MDS theorem. So that, I guess, should also be cited there. And again, we have this lower bound that shows that at least up to this dependence on L, this is the best possible alphabet size you can get. I have about 10 minutes left. So in the last 10 minutes, I'm going to talk about the ideas in our alphabet reduction proof. So to introduce the ideas, I'm going to give you a different way of thinking about why Reed-Solomon codes are unique decodable. Kind of a little bit contrived, but it generalizes to the list decoding setting. So Reed-Solomon codes are optimally unique decodable because van der Waals matrices have trivial kernel, right? So van der Waals matrices, they're matrices that look like this, and they're well known to have trivial kernel, meaning that these kinds of equations have no solutions. And that implies that Reed-Solomon codes are unique decodable because, well, if these having no solutions means there's no, you think of f1 and f2 as vectors of coefficients. There's no two polynomials that, low degree polynomials that agree on too many points. That implies unique decodability after you push around some, do some counting. So so this is probably not how you're used to seeing Reed-Solomon codes are unique decodable, but the advantage of this perspective is that we can generalize this to list decoding. And this is always true, right? As long as these evaluation points are different, pairwise distinct, then this is true. So with this perspective, we can generalize it to list decoding. So we can say a Reed-Solomon code is optimally list decodable if and only if matrices that look like this have trivial kernel. So what is this? So we call these things reduced intersection matrices. This was originally observed by Shangguo and Tama, who work with a slightly different but basically equivalent matrix. And just like how this van der Waals matrix encodes agreements between code words that are too close together, this reduced intersection matrix encodes agreements between code words in a bad list decoding configuration. So here we are thinking about, let's say we're trying to list decode all the way up to capacity, the generalized singleton bound with list size 2. So then you are trying to list decode to this radius. So when would a code not be list decodable? If it's not list decodable, if you've got 3 code words, F1, F2, and F3, that all lie in some small ball. But if they all lie in some small ball, that means they're going to all agree on a lot of different places. And we take these agreements from a bad list decoding configuration and put them in a matrix, just like we have done here. And so if all the matrices that look like this, whatever this means, if all the matrices that look like this have trivial kernel, then all of these equations have no solutions, which means there are no 3 code words in a bad list decoding configuration, which means our code is list decodable. So having our Reed-Solomon code be list decodable is equivalent to having all of these matrices, whatever these are, having trivial kernel. And it turns out that if you're trying to be optimally list decodable, these matrices turn out to be square. And so how do you prove that? So what do you do? We're proving random. We think about these evaluation points as chosen at random, and we show that so for these matrices to have trivial kernel, that's equivalent to the determinant being non-zero. And so the probability for a random evaluation points that any one of these matrices is doesn't have trivial kernel is something like L times K over Q. So this follows from the Schwarz-Zippel lemma. You get the determinant here is some polynomial, and the probability that the polynomial is, assuming the polynomial is non-zero, which you have to show, then the probability that some evaluation points make the determinant 0 is something like this. This is the degree of the polynomial, and this is the field. This is just by the Schwarz-Zippel lemma. Okay. So the probability that one of these matrices has trivial kernel is LK over Q, and then you union bound over all possible matrices that look like this. And if you're union bound, if Q is large enough, then your union bound makes it so that your code is overall list decodable with high probability. So again, Reed-Solomon codes being optimally list decodable is equivalent to these reduced intersection matrices having trivial kernel. If the evaluation points are random, then with high probability, and your field size is large enough, with high probability, they all have trivial kernel, so your whole code is list decodable. So this is like the high level, summary of, this is the idea of the proof for even in the BGM paper. For optimal, so you just replace 2 with a larger L, and this gives you the one caveat here is that the one thing you have to check is that when you take the determinant of this reduced intersection matrix, that it's some polynomial, and you need to make sure it's not the 0 polynomial. And so that's one way to interpret the main contribution of BGM is they show that these determinants are in fact non-zero polynomials. I mean, they do more in their paper, but that's one of the main things. Okay, so why do we have an exponential alphabet size? You look at this union bound. We're union bounding over all the matrices. I haven't told you what the structure is, but it turns out there's exponential in n many matrices. And so how do we improve this? And I think this is an idea that everyone here can appreciate. So what Guo and Zhang first observed is that we're going to relax this by epsilon. So now instead of wanting our code to be list decodable all the way to the exact bound, we can relax it by epsilon. So now what is a bad list decoding configuration? It's a set of points in a smaller ball, which means that the matrices that we care about have, oh, sorry, this should be alpha, are not square anymore. They have a few more rows than they have columns. So they're slightly taller than they are wide. And because we get a few more rows, then it's going to amplify the probability that these matrices don't have trivial kernel. And it's going to amplify it by this factor of roughly omega of epsilon times n. And you might wonder, okay, where does this omega epsilon times n come from? I think it would be helpful to give an illustration in terms of random matrices. So these are random matrices, but they have some structure. So let's think about what happens with a purely random matrix. So what is the probability? Let's say we have an n by n matrix, okay, and all the entries are IID elements of FQ. What is the probability that this has trivial kernel? Somebody? So in other words, what is the probability this thing is full rank? Yes? It's high. What is, sorry? It depends on Q, right? What's the dependence on Q? Yeah, it's something like 1 minus 1 over Q. Yeah, so it's yes, right. So it's more like 1 minus 1 over Q times 1 minus 1 over Q squared times ... 1 minus 1 over Q to the n, or maybe minus 1 or something. Yeah, maybe it's n. Yeah, and so where does this come from? It says that, well, but the whole point is this is dominated by this 1 minus 1 over Q. And where does this 1 minus 1 over Q comes from? You imagine you generate this matrix, one row at a time, and each time you add another row, you want it to be in, not in the span of the previous rows. So this 1 minus 1 over Q is the probability that this last row is in the span of the previous rows. And so that's where this 1 minus 1 over Q comes from. Now let's consider, the analog of this, where now we have an n by n times 1 plus epsilon n matrix. Okay. And now, again, the entries are IID, over FQ. What is the probability that this has trivial kernel? Right? It's super small, right? So now it's going to, you have, epsilon n extra rows. like if this one is in the span, well, you have epsilon n extra rows to sort of be not in the span. So it's going to be something like 1 minus 1 over q to the epsilon n. And I actually don't know. Maybe just to be safe, I'll put an omega here. So for random matrices, when you have something squared, you get this 1 over q, just like we had here. And then when you have just a few more rows than columns, then you can amplify the probability that has a trivial kernel. And so this happens for purely random matrices. Here we are looking at random matrices that have some structure. But it turns out, and what Guo and Zhang showed, and what we refined their techniques to get a better bound for, is that you can, in fact, do the same kind of argument here and amplify the probability. And so what do we need? We just need that these rows are kind of, you can kind of group the rows into a bunch of different groups that all are kind of independent, right? This row is independent of this row, and so a lot of these rows, you have a lot of independence, and so you can still do this kind of argument where you generate the rows one at a time. All right, so that's all I wanted to say about how we reduce the alphabet size. And so the last slide is just kind of more of a pitch for what I think Gopi is probably going to talk about tomorrow, which is that there's one thing left, which is that we need to show these reduced intersection matrices have to be full rank as formal polynomial matrices. So the way that they do that in this BGM paper is they have this higher order MDS notion, and they show that this notion and this GM MDS notion, and also something about maximally recoverable codes, these are all kind of equivalent. They're all equivalent, and it was known in this GM MDS theorem by Lovett and independently by Yildiz and Hasibi that Reed-Solomon codes have this GM MDS property, and because of this equivalence, that Reed-Solomon codes are also optimally list-decodable because these matrices are indeed full rank as formal matrices. So one thing we do kind of in the appendix of our work is we give maybe another interpretation of, so what they do is they have like a combinatorial part of their argument and an algebraic part. And what we show is that what they do in their combinatorial part of the argument, they kind of do it from scratch and with their bare hands. And what we observe is, and this is that what they actually proved combinatorially is actually quite difficult. It's this result about orienting hypergraphs that have some partition connectivity condition that is well studied in operations research and in other communities. And so, yeah, this is a very impressive work in a lot of different ways. And but there's, if you want to see, yeah, so in our paper, we have this description of how you can go straight from list decoding to GM MDS using this hypergraph orientation language. Okay, so that's all. So just to summarize, I introduced list decoding, told you about the list decoding capacity theorem and how we have this problem of trying to find hay in a haystack. And I told you two stories about going towards that. So we talked about list decoding random linear binary codes and list decoding Reed-Solomon codes up to capacity with optimal linear size alpha. That's all, thanks.
Questions? That's too clear.
I have one question about the first part at the top, which is, so is there any reduction, because it seems like having optimal list decodable binary codes is much harder than codes achieving capacity with on BEC, for example, right? Is there a reduction, like formally, let's say I have a explicit or a code which achieves the list decoding capacity, can I prove that it also achieves BEC capacity?
So the question is there some formal reduction from a code achieving capacity on the BEC to codes that achieve list decoding capacity? Right. The capacity is the same, and so it's a good question. So my reason for believing that the answer is no is so I would be doubtful, and one reason is that, well, if you did it, it would have to somehow use the fact that you're in the Hamming metric. Because if you do it for deletion codes you can't correct more than half fraction of errors, but random deletions you can correct all the way up to 1. So there's, at least if you did it for deletions, you can't have this correspondence. So maybe that's a reason why you can't do it, at least in like some super black box way for list decoding.
But it's possible for Hamming metric, it's
It's
possible.
possible for Hamming metric, yeah.
So for capacity, we have a connection to the weight enumerator of the code. We don't have such a thing for list decoding other than the trivial Johnson band. So that's one of the areas.
Other questions? Oh, yes.
So I guess the question is like, okay, you're using randomness to basically pick these evaluation points of your code, right?
Yeah.
And so I guess in terms of getting like an explicit code, you would then need to just find evaluation points.
Yes.
Such that like all these matrices.
Yes, that's correct.
Subset of the points of size, whatever, like L or something,
Yeah.
the size is full rank.
Yeah.
Okay.
Yeah, that's
And
right.
that just seems to be pretty challenging.
Yeah, that's right. I think Gopi has some work where they do that for, I don't know, dimension 2 or something, or
Which ones?
explicit Reed-Solomon codes for some,
Right.
when the like, yeah, list size is 2 and dimension is 2, something like that.
I guess there are always these sort of kind of inefficient ways of just keep on taking new points from like higher and higher extensions. Can you do that sort of trick here?
Yes, so there is a mathematically explicit construction where you take these, but then the field size is double exponential in n.
I know, I'm not saying it's a good
That's
solution,
in the
but
ST20 paper.
Yes, in the ST20 paper.
no more questions?
All right.
Okay, thank you. Yeah, 4:30 at the main entrance. If you want to.